Here are a few party questions from the paper Statistical Mechanics. We may discuss them one by one. First question is state zeroth law of thermodynamics. If bodies A and B are in thermal equilibrium with the third body C, then they are in thermal equilibrium with each other. A and B are separately in thermal equilibrium with C. Then the three are in thermal equilibrium with each other. The consequence of zeroth law is temperature. State the first law of thermodynamics. The heat energy given to a system is equal to the sum of change in internal energy of the system and the external work done by it. Del Q, the quantity of heat energy given, is equal to du, change in internal energy, plus external work done. Here for heat and work done, we have given inexact differentiation delta. But for internal energy, we have given exact differentiation. Because heat and work done are path function, whereas internal energy is a state function. Then del W is replaced by pressure into change in volume. So this is the first law of thermodynamics. Consequence of first law is internal energy. Now give the Kelvin statement of the second law of thermodynamics. It's impossible to get continuous supply of heat from a body by cooling it to a temperature lower than that of its environment, is our Kelvin statement. According to Clausius, it's impossible for a self-acting machine unaided by any external agency to transfer heat from a body at a lower temperature to a body at a higher temperature. It's impossible to transform heat energy from a cold body to hot body without the help of any machine. If the machine is self-acting, that will not be used to transform heat energy from cold body to hot body. We need an external agency. In the case of refrigerator, we have achieved this. With the help of compressor, we are transforming heat energy from the cold body to hot body. State the third law of thermodynamics. At absolute zero, entropy approaches zero. This is our third law of thermodynamics. But the attainment of absolute zero is practically not possible. Therefore, entropy is also existing. What are thermodynamic potentials? The functions internal energy, enthalpy, Helm free energy and Gibbs free energy in thermodynamics play the same role as played by potential energy in mechanics. Therefore, they are called thermodynamic potentials. Define the term internal energy. Heat content of a system at constant volume is called internal energy, whereas the heat content of a system at constant pressure is called enthalpy, H equal to U plus PV. Define Helm free energy. Helm free energy and Gibbs free energy are available forms of energies. Helm free energy, F is equal to U minus Ts. Here U is the internal energy. The product temperature and entropy is a form of unavailable energy, the energy which cannot be converted into mechanical work. The change in Helmholtz free energy is exactly equal to the maximum work done in isothermal changes. Define Gibbs free energy. G equal to H minus Ts is Gibbs free energy. Gibbs free energy remains constant in an isothermal isobaric process. What is entropy? The thermal property of a body which remains constant during an adiabatic process. When no heat energy is given to or removed from it is called entropy. So in the case of isothermal process, temperature remains constant. Isothermal in an isothermal process, temperature is constant. In an adiabatic process, entropy is a constant. Entropy is constant. So the change in entropy is equal to del Q by T. The quantity of heat energy either given to the system or taken away from the system divided by its temperature. This is called the change in entropy. How does the entropy change in a reversible process? Suppose a system passes from A to B along the path C1, the change in entropy ds integral limit varying from A to B equal to del Q by T integral A to B. If you integrate this ds, we can get S, and if you apply the upper limit, that is SB, lower limit is A. SB minus SA equal to integral limit varying from A to B delta Q by T. Suppose the system passes from A to B along the path C2. If the system is choosing this path, you can get the same result. SB minus SA equal to limit varying from A to B delta Q by T. See, because entropy is not a path function, it is a state function. Entropy is independent of path. Then we may change this integral limit varying from B to A delta Q by T with a negative sign. See this? Integral A to B delta Q by T is changed as minus of integral B to A delta Q by T. If the system passes from A to B along the path C1 and comes to the initial state A through the path C2. See here, if the system passes from A to B along the path C1 and comes back to A along the reversible path C2, then the total change in entropy is delta Q by T A to B plus del Q by T A to B. See here, the lower limit is A, upper limit is B. In the return journey, the lower limit is A, upper limit is B. See here, this is forward journey, A to B. Then this is return journey. Here the lower limit is B, upper limit is A. Instead of this del Q by T A to B, we may put minus of integral B to A del Q by T. If you add these two things, you can get 0. Therefore, the change in entropy for a reversible cycle is always 0. That means that in a reversible cycle, entropy is a constant. What do you mean by the concept of increasing entropy? Consider an irreversible process such as conduction and radiation. in which a body loses heat at a temperature T1 and gains heat at a lower temperature T2. Let Q be the quantity of heat lost at a temperature T1 and the amount of heat is gained at a temperature T2. Del Q by T1, del Q by T2. Now, gain in entropy of the cold body is Q by T2 because the cold body is at a temperature T2. Loss in entropy of the hot body is Q by T1. Change in entropy ds equal to gain minus loss, that is Q by T2 minus Q by T1. Here T1 is greater than T2. So this is smaller value, this is greater value. So the subtraction result is a positive quantity. Therefore ds is greater than 0. So the entropy increases. The change in entropy is greater than 0 means entropy is not a constant, it is increasing. As we see that in an irreversible cycle, there is always a net gain of entropy. That means entropy increases. With the help of these two, we may form an inequality called the Clashes inequality. ds greater than or equal to 0. If the process is reversible, ds equal to 0. ds equal to 0 means the change in entropy equal to 0. That means differentiation of entropy equal to 0, which means that entropy is a constant. If you differentiate a constant, we can get the 0 result. Suppose the change in entropy is greater than 0, it specifies an irreversible process, which means that the entropy increases. This is called Clashes inequality. What's the role of Clashes-Clapeyron-Lennard equation? The boiling point and melting point of a substance depend on the pressure. According to Clapeyron-Lennard equation, dP by dt equal to L divided by T into V2 minus V1. Here L is our latent heat, V2 minus V1 is the change in volume. Effect of pressure on the boiling point and melting point is studied with the help of the Clapeyron-Lennard equation. What's the effect of pressure on melting point of a solid? We know that dP by dt equal to L divided by T into V2 minus V1. L is the latent heat, V1 is the initial volume, V2 equal to final volume. When V2 minus V1 is a positive quantity, dP by dt is also a positive quantity. At that stage, the melting point increases. Example, wax. If you take the wax in the solid state, its volume is V1. Convert this wax into liquid, its volume is V2. Here, V2 minus V1 is a positive quantity, which means the volume of wax arrived in the liquid state is greater than that of the volume of wax taken in the solid state. Therefore, if V2 minus V1 is positive, dP by dt is also positive. If you increase the pressure, the melting point of wax is also increased. But if you go to the conversion of ice into water, ice to water, V1 is the volume of ice, V2 is the volume of water harvested, V2 minus V1 is a negative quantity because the amount of water, that is the volume of water arrived is lesser than that of the volume of ice taken. Therefore, V2 minus V1 is a negative quantity. Suppose V2 minus V1 is negative, dP by dt is also negative. As a result of this, on increasing the pressure, the melting point of ice decreases. So the ice is started to melt before reaching 0 degrees Celsius. What's the effect of pressure? on boiling point of liquid. On increasing the pressure, the boiling point always increases. Derive the second Latin equation. Say the change in entropy ds equal to delta Q by T. For a phase transformation, say for example liquid to upper state is concerned, the delta Q is our latenate, ds equal to S2 minus S1. So S2 minus S1, that is final entropy minus initial entropy, which is equal to, instead of this del Q, we have to substitute latenate L by T. Now differentiate with respect to T, ds2 by dt minus ds1 by dt equal to, if you make our differentiation by keeping L as a constant, you may get L into minus 1 by T square, that is minus L by T square. If you keep T as a constant, this is 1 by T into dl by dt, u by v, we have to apply two variables. So that this is the differentiation result. Then multiply both sides with the help of T, that is T into ds2 by dt minus T into ds1 by dt equal to minus of L by T plus dl by dt. Here T into ds2 by dt equal to specific heat in the vapor state, that is C2. The quantity of heat energy required to raise the temperature of unit mass of the substance through 1 degree is called the specific heat. T into ds1 by dt is equal to specific heat in the liquid state, that is C1. So C2 minus C1 equal to dl by dt minus L by T. This is called the second latenate equation. Write down van der Waals equation of state. For a perfect gas, that means a gas which obeys Boyle's law and Charles' law, we may write PV equal to RT. But at high pressure and low temperature, PV equal to RT is not valid. That means in practice, no real gas obeys the gas laws perfectly. Therefore, correction is needed. Correction for pressure is P equal to A by V square. Pressure is proportional to rho square. Pressure is then inversely proportional to V square. Because mass by volume is density. So pressure is directly proportional to rho square, means it is inversely proportional to volume square. To remove the proportionality sign, we are introducing constant A. So P equal to A by V square. Now we have to give the correction P plus A by V square. In this equation, instead of P, we have to put P plus A by V square. Then correction for volume is B. That means V minus B. The average volume available for each molecule is V minus B. B is 4 times the actual volume of the molecule. So instead of V, we have to put V minus B. Now the equation PV equal to RT is modified as P plus A by V square into V minus B equal to RT. This is called van der Waals equation of state. What are the assumptions considered in an ideal gas? The molecules are mere mass points and occupy no space. That is, volume occupied by a molecule is negligible. There is no force of attraction or repulsion between the molecules. By considering these two cases, they derived the relation PV equal to RT, but in actual practice, these are all violated. What are critical constants? Vc equal to 3b, Tc equal to 8a by 27 rb, Pc equal to a divided by 27 b square are the values of critical volume, critical temperature and critical pressure respectively. Critical temperature is a temperature above which gases cannot be liquefied. On liquefaction of gases, the temperature of the gas should be lesser than the critical temperature. If the temperature is more than that of the critical temperature, we won't convert the gas into liquid. Critical pressure is a minimum pressure which must be applied at critical temperature to convert the gas into liquid. Even though the temperature is equal to critical temperature, and if the pressure is lesser than the critical pressure, liquefaction will not be taken place. Then the critical volume. The volume occupied by 1 mole of gas at critical temperature and critical pressure is called critical volume.